Hello, this is Juan Pedro Llerena, and I have the pleasure to introduce you our work and approach to forecasting and filtering noise and dynamic systems using LSTM architecture. Before to start, I would like to present you our working group at Carlos III University of Madrid. The Applied Artificial Intelligence group is centered in all kinds of artificial intelligence applications, such as automatic learning techniques, computer vision, or data fusion system. This work has been made by Jesús García, José Manuel Molina, and this speaker, Juan Pedro Llerena. Our work addresses state filtering problem from deep learning paradigms. From human perspective, movement estimation is based on previous observation and the intuition coming from the previous observer knowledge. In this way, practically everybody who sees a bicycle passing calmly can sense where it will be after a few moments. These mechanisms allow us to play tennis, walk among people without crashing, and in general to do every action of daily life. From the machine's perspective, the same bicycle example requires a perception phase using sensors that have central accuracy, a dynamic model, and a methodology to allow knowing previous state with noise, such as position or speed, and a dynamic model estimate the future state not yet measured. These problems are widely studied in estimation theory and mainly are based on state space model and statistics theory. However, a state space model can have difficulty to model certain complex systems. They are not able to model long-term relationship, or the convergence of time of filters can be too long. In order to propose new solutions to state space model difficulties and to search new estimation methodology to continue solving classical challenges, we address the estimation problem of uniform rectilinear motion with position measurement under a certain Gaussian noise from deep learning paradigms. Our neural system is compared to the optimal Kalman filter system with the root mean square error matrix. This proposal implies facing certain difficulties presented by the estimation model with the neural network such as saturation in prediction outside the training space. We tackle the saturation model using sliding window with overlapping area and normalization this sliding window data. Also, this overlapping area allows keep long-term temporal trends and help to activate internal state of the artificial neural network. To train artificial neural network in prediction and filtering, data batch phi are composed by ideal state X and noisy state zeta. Ideal and measured state series are organized one time position displaced to shape one batch. Finally, we use mean square error as a loss function to optimize our neural architecture function. This work is developed under following guidelines. Firstly, we generate a synthetic database. These data are divided and preprocessing. In parallel, we develop a neural architecture. This model is validated and compared with Kalman filter. Finally, we simulate two experiments with new trajectory. The database is composed by 1000 simulated trajectories with different initial conditions selected randomly with the criterial table 1. Then, we select not overlapping consecutive time window over each path to split data set between training and validation. Finally, each series are normalized. As for the artificial neural architecture, our architecture is composed of a single variable sequence input layer with 18 samples, an encoder-decoder system composed with 400 and 200 LSTM cells, respectively. The internal interconnection layer is composed by 16 ReLU units with 20% dropout fully connected. Finally, the output layer is fully connected layer with one output unit. About Kalman, this initialization is done after the second position measurement to obtain by difference the second state, speed, and the covariance matrix. At the validation stage, our model and Kalman is tested in two different checkpoints with the validation set. The first is located after the activation region of the validation series, always with the measurement difference. The second checkpoint is done with the last filtered measurement. This checkpoint selected is justified based on Kalman words and best estimate after the activation region required to activate network. Understanding by activation a transitory state of network required to adjust internal network parameters. Applying this checkpoint to the validation set, we can see how for the first checkpoint, Kalman's filter has not managed to converge yet, and it's improving in estimation by LSTM model. At the second checkpoint, Kalman estimation error is less than LSTM. We make two simulation experiments. The first one simulates filtering with new signal from uniform rectilinear motion when the system is in feedback with new continuous measurement. In the first time window, we can see how the network gets quickly error level and presented the low errors root mean square error than Kalman. Kalman decreased his error with the exponential trend. During the second time window, after the overlap region, we can see how Kalman trend to the optimum with the network get his error limit. On the second experiment, we simulate loss experiment in two different moments. The first one after the first activation area with the first time window, and the second one after the overlap area with the second time window. In the first case, we can see how the few measurements Kalman filters can decouple, while the neural network keeps his error limit. In the second case, although the filter has reduced its error, a small error is decoupled the system, but Kalman has lower root mean square error than LSTM. In conclusion, we implement an error estimator filter architecture inspired by encoder-decoder system with recurrent LSTM cells. Our model was compared with the Kalman filter along two time windows, showing at the first time the LSTM model improved the results in filtering and estimation than Kalman, after it showed evidence of a limited error. To some extent, the LSTM model has more information from unstandardization than Kalman filter. This is done to find the minimum system error level. The proposed methodology can be an alternative if we have a structure and validate data about the dynamic system. Kalman filter continues to be more robust with continuous measurement for longest time period. As future work, we propose to use this methodology to solve problems with highly nonlinear dynamic system and or not Gaussian measurement or non-Markovian dynamics. Thank you very much.